Okay, I am going to go ahead and start the meeting. Um, it's a pleasure to welcome everyone to the first MoveIt community meeting. This is the first time we've done this, and the response has just been incredible. There are more than 200 people registered, and I certainly didn't expect such a huge response. So thank you, and hopefully you'll find this meeting useful. This is the agenda for the meeting. We've got 7 talks and time for discussion at the end as well. If you have questions during each talk, please type your questions for the presenter in the chat window, and I will ask the questions. At the end, type your question for the discussion, type your question into the chat window again, and I'll unmute you so you can ask the question. This meeting is being recorded and will be available online soon. We will also make slides available online so people who haven't seen the meeting can get access to that as well. So I'm going to go ahead and start talking about MoveIt. This is the first talk of this MoveIt community meeting, and I'll give you an update on where we are with MoveIt. MoveIt must be doing well. There are more than 200 people registered for this talk. That is way more than we thought would register when we first advertised this talk, for sure. So thank you everyone for coming online and spending time with us. These are brief set of statistics. Based just on number of installations, this is just based on the number of visits to the MoveIt install page. It's over 10,000 this year itself. The number of users on the mailing list has grown to 693, up from 177 in 2013. I know there's a huge number of robots with MoveIt used on them. If you use MoveIt on a new robot, make sure to let us know on the MoveIt users mailing list. And in the most recent ROS survey, MoveIt was ranked number 3 on the list of important ROS packages after RViz and navigation. Thanks a lot to all the contributors who have been working to keep MoveIt active and contributing code, answering questions. I don't think I've mentioned everyone here, so if I've omitted your name, please forgive me. Just send me an email and let me know, and I'll make sure to update the slides. In particular, I'd like to thank Mike Ferguson for taking on the responsibility of doing the releases. It's a heavy responsibility, and we owe him a debt for doing this in both Indigo and Jade as well. There's been a bunch of new features, all contributions from the community. This is over 2014 and 2015. And again, I might have missed a few new features here, so let me know over email if I've missed anything. There's a new Cartesian Path Planner plugin from the ROS Industrial Consortium, a new trajectory display plugin for RViz from Dave Coleman, trajectory velocity scaling from Stefan at Team Weiger, joystick interface from Rohe and Dave Coleman, a plugin interface for collision detection, and also recently updates coming through to the point cloud Optomap updated as well. There's of course a ton of robots, new robots that are running MoveIt, and again, If you use MoveIt with a new robot that maybe is not yet included in the list, make sure to send us an email on MoveIt users so we know about it, and we can add it to the list of robots. It seems like there's a lot of interest in mobile robotics and definitely in humanoids, but we've also seen MoveIt used on unique new robots like an underwater robot, and we're going to see a talk about that as part of this meeting as well. MoveIt is also being used in education a lot. Matej Chokerle at Columbia University taught a course using MoveIt, and if you're using MoveIt as part of your courses, again, please let us know on the MoveIt users mailing list. If you can share course material, that would be great too. There's a ton of applications that have been developed on top of MoveIt, and I just put in a few here. I'm sure there's a ton more that I could have listed. A pretty unique one is path planning for transmission electron microscope. So not traditional robotics the way we think about it, but a different place in which MoveIt and motion planning is being used. Of course, in the DRC, we saw a bunch of different humanoid robotics teams using MoveIt. We also saw it being used at the Amazon Picking Challenge. And like I mentioned, we'll see a talk about its use in underwater robotics as well. There's a lot of papers published that have been referencing MoveIt. And if you do use MoveIt, please do make sure to cite MoveIt in your paper. Just in ICRA 2015, we had over 11 papers that cited or used MoveIt in some way. This is a chart that I made just looking at citations for different open source software at ICRA 2015. I just looked at software that was related to manipulation, and of course this is heavily biased towards the ROS ecosystem. And this gives you an idea that ROS has been cited over 100 times at ICRA, and it's out of about 800 to 900 papers, I believe. We definitely see that there's a lot of activity around open source, and we definitely love to see these numbers go up for all the packages. There's been a lot of events in which MoveIt has been used, like I mentioned, the Amazon Picking Challenge, the Darpa Robotics Challenge. At ROS-Con in a month, Dave Coleman will be giving a long talk on MoveIt strengths, weaknesses, and developer insights. So if you're at ROS-Con, I would encourage you to go to his talk and send feedback on the MoveIt users mailing list. We definitely cannot do this alone. MoveIt is supported now entirely by the community. There is no one core set of funding for MoveIt or core organization that is funding MoveIt. So we definitely could use all the help that we can get. The first thing is just the MoveIt website. We'd like to port it to GitHub pages. If you have experience with that, please email me to help out. The tutorials are not up to date with the latest version. If you're willing to write new tutorials, or as you do your projects, please generate pull requests and update the tutorials so that all of us can get more up to date with how to use MoveIt. Our goal is to make MoveIt a better tool for research, and the way we're going to start doing that is to coordinate the community around a few features every quarter. So the goals for the end of this year are to integrate better support for humanoid kinematics. That's for robots like the Robonaut, There's new benchmarks updates which would help all of us in terms of benchmarking some of our code, and these are coming from Lydia Kravarty's lab at Rice Universities, and we'd also like to resurrect support for other types of planners. So example, STOMP, and you'll see some information about that today. If you want to contribute, join the MoveIt mailing list. You can easily get to it off the MoveIt website as well. Please do send us news for the blog. There are 200 people on this call. I'm sure all of you have some movies of how you've used MoveIt at some point. We would love to hear about that. So send us movies of projects, robots, anything you want. If you want to contribute, write MoveIt development support into your grants, fund your students to work on MoveIt, and have them contribute back. That would be the best way to contribute code, develop tests, write tutorials, so we can make MoveIt the kind of software that can be used on a huge number of robots. In the future, we're looking at better integration with ROS-Control, better integration with grasping tools, and as ROS 2.0 is coming online, we'll also start looking at how MoveIt can be upgraded to use ROS 2.0. And of course, we'd like to add more support for mobile manipulation as well. So manipulation in ROS is a huge thing. I just drew kind of a schematic of how it looks like. There's MoveIt, there's a ton of other components that play a part. FCL for collision checking. You'll hear about OMPL in a minute, STOMP, other motion planners, and of course ROS-Control as well. So it's not MoveIt by itself, it's a huge community of packages, and I would encourage you to contribute and support all of these so we can build more cool applications. We plan to hold this meeting every quarter. So tentatively, January 2016 would be the next meeting. And we'd like to see if we can co-locate it with conferences. So if you have suggestions, please let me know. And if you have any questions at all, feel free to send me email about anything regarding MoveIt that you want to know. Thank you very much. And I'm going to now switch over to the next presentation, and we probably have just a minute for questions if somebody has them. Hey, Mark, I think you can go ahead.
Okay. This is Mark Mol from Rice University, and I'll give you a brief overview of what OMPL is about and what you can expect in the upcoming release. So I don't have a whole lot of time, so I'll give you a very brief overview of what OMPL is. It's the default planning backend in MoveIt. So if you're using MoveIt, then most likely you're also using OMPL. It provides a common core for sampling-based motion planners. So it's important to keep in mind that there's nothing in OMPL, well, there's nothing in the abstract API for planners that forces it to be limited to sampling-based planning. So it's possible to add heuristic-based search or optimization-based planning methods to MoveIt as well. But when we designed OMPL, we really wanted to make a library that was easy enough to use for education, but at the same time, so it contained state-of-the-art algorithms and was sort of robust enough to be used in industry. So yeah, the basic workflow in MoveIt is that we take models of the robot, take sensor data of the world, construct a model that we can then plan in, produce a path that can then be passed on to ROS-Control to be executed on a robot. And OMPL is sort of providing the abstract algorithms and MoveIt the integration with the rest of ROS. So yeah, OMPL is a C++ library with extensive Python bindings. It tries to provide very fair and sort of accurate implementations of all the known algorithms in the sampling-based literature. Currently, there are over 35 different sampling-based algorithms going back to the very first ones like PRM and RRT, and algorithms that are just being published or aren't being published yet. We can roughly categorize them as sort of multi-query, single-query planners, planners that try to provide some kind of optimality guarantees, and dynamic planners, although the last category isn't supported in MoveIt at this point. And we try to provide very high levels of abstraction for things like state spaces, that we don't assume that they're Euclidean, metric, or even continuous. State validity is more general than just collision checking. You can have very complex constraints of what it means for a robot state to be valid. And we also have tried to generalize this notion of path optimization. It doesn't necessarily mean path length. And finally, we have built-in extensive benchmark facilities, and I'll come back to that later on. So we have a release coming up in the next couple months. We don't have a firm deadline, but these are some of the things that we will definitely be included. A bunch of new planners, but two are called Thunder and Lightning. They're based experience-based planning methods, and I'll talk more about that later. Then we have a number of optimizing planners, informed RRT star and batch-informed trees, which provide asymptotic optimality. And then there's LBT RRT, that provides approximately asymptotic optimality, approximately near optimal optimality. So slightly weaker condition, optimality condition, but hopefully better runtimes. Then there's a new version of TRRT and a bidirectional version of that. Another different thing is goal optimization and path optimization. What it really concretely means is that if you get a path back that happens to have a bad IK solution for your goal, then the optimization can sort of take care of that and try to fix that up while still keeping a valid path. We've noticed that a lot of the optimizing planners spend a disproportionate amount of time in nearest neighbor queries, so we've spent some time on trying to optimize that a little bit. And finally, we have some new web-based interface for planning that integrates also with our net benchmarking capabilities. Okay, so I won't have time to talk about everything that I just mentioned. I'll just talk briefly about just a few selected highlights. One of them that is the Thunder planner developed by Dave Coleman in collaboration with Johan Sukan, myself, and Kei Okada, and Corel from University of Colorado. What it is a experience-based planning framework, and what it means is that it's trying to improve its performance over time by comparing any new motion planning requests with motion planning requests that were solved previously. So when you get a motion planning request, it will in parallel try to plan from scratch and try to find a similar motion planning query that was solved previously and deform the previously found solution to fit the new motion planning query. And so these two threads are running in parallel, and whatever finishes first terminates the other thread and will produce that, send that path to the robot. The path will also be possibly stored in the database, but we have a filter to make sure that the path is sort of different enough from previous motion planning requests. So we want to bound the growth of the database. So this was tested on a humanoid robot, lots of degrees of freedom in various different scenes. We wanted to show that if you have a robot that is forced to stand on one leg and has to move from any random pose that is balanced to another balanced pose, we can do better and better over time, even as the scene is changing. So this is a 30 DOF robot, very complex scenes, and we have shown that this really works much, much better than Lightning, which is an algorithm similar in flavor, but doesn't have some of the nicer properties of Thunder. And we can see this if you look at the top graph, planning time that converts to planning times of less than a second, whereas planning from scratch will take you 10.5 seconds, and planning with Lightning is around 8.5 seconds. So Lightning saves you some time, but Thunder really has a better reuse of previous experiences. And the second graph shows that very directly. We look at what percentage of the solutions were produced by looking it up in the database and which percentage was produced from planning from scratch. So with Thunder, we see that it converts to nearly 100% recall from the database, and Lightning bottoms out at like 46%. At the same time, even though we have all this recall, we don't really have a huge database to maintain. The bottom graph shows that we essentially bound the size of the database, whereas with Lightning, it doesn't have this property of trying to minimize the storage. So now let's switch to a different planner. This is Informed RT Star, an asymptotically optimal planner. There's many planners like this now in OMPL. And this is the sort of a very recent version of this that's using heuristics to guide the search and where to sample next. So once you have found an initial solution, we can bound where the optimal solution can lie, and we can restrict the sampling to just the bounded area. So in this case, we're looking for path length, and we can bound the optimal solution to an ellipse, but all the states have to lie within that ellipse. And as we find better and better solution, we can tighten that ellipse until essentially we have a straight line in this case where there's no obstacles. Batch Informed Tree is an improved version of this, and it generalizes some other ideas that have been around in optimizing planners. It can be seen as an extension of incremental graph search techniques like lifelong planning A-star to continuous domains. At the same time, you can also think of it as a generalization of RT star and FMT star. So you can sort of, by varying some parameters, you can make bit star behave like RT star or FMT star. And that's from a very recent paper in ACRAF 15. Now let's switch to something else. We've developed this web-based planning framework that you can visit right now and try it out. You can upload your own meshes and do a basic rigid body motion planning. We've built in some models for car-like systems as well, so you can play around with that. It's not arbitrary dynamics at this point. This is really to show that you can do simple planning just through the browser without installing any software. You can run it locally too if you want. And the hope is that eventually we can have something working like this for MoveIt as well. We can have a MoveIt front end to just configure benchmarks and try that out on some cluster or powerful server. So once we have solved these problems, we can integrate them, and we can also configure benchmarks and send it to our benchmarking server. And afterwards, you can then browse the results. You can say, well, I'm interested in particular kinds of problems. I want to see how various planners perform on these problems across various metrics. So we've documented the sort of log format for this benchmarking infrastructure, as well as the benchmarking database that we construct from those logs. So you can really try to build it into any other planning library if you want to. And you can upload your own benchmark data here. So all this stuff you can run locally, but we have a server. It's planarena.org. For MoveIt, there are a few things that you need to add to be able to use these benchmarks. Ryan Luna has developed sort of an improved version of MoveIt benchmark so that you can use all the benchmarking facilities in OMPL in MoveIt and visualize the data on our server. So I think that's very exciting. And finally, I'll just conclude with some pointers to where you can get more information, where you can get the code, and where you can reach us. So I'll stop here and take any questions.
Do you have any questions for Mark?
Yes.
Please type them into the chat window, and I can ask them. I'm going to Mark. I'm going to upload Adolfo.
Okay.
We can do the next one.
Okay. Hello, everybody. So I will be talking about what's new in the ROS-Control project. I'm going to basically split the talk in two parts. I'm going to first talk about the new features that have been incorporated into ROS-Control. And then in the second half, I'm going to talk about some quality assurance metrics of the project. So just to give a little bit of context, ROS-Control is a project that has as a basic aim to lower the entry barrier for exposing hardware to ROS, and also to make it easier to simulate it. It also aims at promoting the reuse of control code in the same spirit that ROS has done for higher level software. So you can picture ROS-Control as this orange region in the image that is between application code and hardware. And also, because we're talking about robot control, the implementation of ROS-Control has been made real-time ready, in the sense that if your application has real-time constraints, then you can use ROS-Control with it. If you want more details, there's last year's ROS-Con talk that you can check out. And I'm going to take the discussion from where we left at ROS-Con. So the first feature I'd like to talk about is what we call the runtime joint mode switching. And what this basically means is that some robots allow you to control the resources, the joints, in different control modes, such as an arm that you can send position, velocity, or effort commands. And with this feature, what you can do is that online and in a transparent way, you can switch from one control mode to the other. And this is very useful for implementing reactive behaviors, such as you're following a trajectory and then something happens, and then you would go, say, into gravity compensation mode. The next feature I would like to talk about is multiple interface controllers. And this is, although the image is similar to the previous slide, it's not exactly the same. So what we can do here is that from a single controller, you can claim resources from different hardware interfaces. So say that your robot has some velocity-controlled wheels, but also has a position-controlled arm. From a single controller, you can have access to all of those resources. And this might seem a little evident, but until not so far ago, you could only claim resources from a single interface in a controller. So I think that that's also really cool. And because it breaks some ROS and C++ APIs, we've decided to roll this only in Jade, not in Indigo. Something else that I'd like to talk about is that we can now specify update periods on a per controller basis. So this is optional. You're not required to do it, but by default, all the controllers update at the same periodic rate, which is the update frequency of what is called the controller manager. But if you can specify a specific option, then you can have controllers that update at slow rates, and this allows you to save some computational resources. Another interesting thing is that we already had before an RQt plugin, which is a Qt-based user interface that's called the RQt Controller Manager, which allows you to graphically interact with the controller manager. This was contributed some time ago by Kelsey Hawkins from Georgia Tech. And what we did now is that we revamped the user interface. And this screenshot that you see here is how it looks right now. So you can, in a glimpse, have a look at all the controllers that are available and their state. So it's like a read-only mode. But then you can do actions like right-click or double-click, and then things happen. So for example, you can have this context menu that allows you to start or stop a controller, load, unload. And then you can have more detailed information about a controller. So if you say, okay, this controller is running, but what type of controller is it, or what kind of resources it's claiming? We're deploying this also in Jade, because as you can see on the right, it now supports controllers with claiming from multiple hardware interfaces. So with this, we conclude the first part, which is new features. And now let's take a quick look at some quality assurance metrics. So what we did is that we took the Jade development branch and we ran some code coverage analysis. And what I'm presenting here is line coverage on a per package basis. The first thing that you can see is that there are quite a few packages that have pretty decent coverage values. Those bars that are in green represent more than 90% code coverage. At the far left, we can see that there is one package, Control Toolbox, that could use some love and get a better test suite. But otherwise, it's looking pretty good. But still, there's a couple of additional things that I would like to mention. One is that if you see the stars here, there are two packages that have very high code coverage, but they actually don't have a test suite of themselves. So they are in fact tested indirectly by other packages. So definitely a point of improvement here would be to give these packages their own tests, because there are some specific cases that actually stress the specific implementation. But still, we're getting decent coverage for those packages, so that's good. But well, every project has its own dirty little secrets, so I'm going to show you ours. I was actually in this graph not showing every single package. There are actually 6 additional packages that have absolutely zero coverage, and they're mentioned here. It's basically 5 controllers and the gazebo bindings. There is a reason for this distribution, which is basically, at least at Darpa Robotics, we have a very strict policy for QA. So most of the packages that you see here with high coverage represent the packages that actually we use in a real-time code path and that are used to move hardware. So a big effort was spent on having good QA metrics on the real-time code path. So definitely the next step would be now to extend this to other packages that at least we are not using to move hardware. And actually, as we speak right now, we are actively working on improving the gazebo bindings. And just to conclude, I would like to acknowledge the contributions of the Factory in a Day project that has been supporting many of the features that I've been discussing so far. So if you have any questions, I'll be happy to answer them. Thank you.
Yeah, Adolfo, there's a question from Jackie asking, can you talk more about how the real-time QA tests in ROS-Control work?
Okay, I'm not sure if I understood the question correctly, but my understanding is that Jackie's asking whether we are checking compliance with real-time constraints. And the answer is no. Yes. So the answer is no. What we are actually checking is that the logic is correct and that the behavior is as expected. So we currently don't have, as part of the test suite, tests that guarantee that no memory allocations are being made or that timing constraints or deadlines are met. We test this on a more informal fashion in-house by running the test suite on a real-time deployment, but there is no automated way of like checking that real-time constraints are not violated.
Can you say a little bit more about which real-time systems you've been using this with?
Yes, we have deployed ROS-Control-based systems on RT Preempt, so this would be soft real-time, and we also have deployed quite a few systems with Xenomai, which is a dual kernel approach, which allows you to have hard real-time.
Okay, and for people who are building new robots, is the wiki page the first place to go to learn more about ROS-Control?
I would say that I would recommend going to 2 places: the wiki page on the ROS wiki, but also the ROS-Con talk from last year. Actually, there's a lot of information from the ROS-Con talk that is in slides and a video that should make it to the wiki, but it's something that just hasn't happened. So I would definitely also recommend checking out the ROS-Con presentation.
So very quickly, a couple more questions. What do you see as really missing from ROS-Control right now?
I'm going to take this opportunity to make a plug. Jackie and I will be presenting at ROS-Con a talk that will address this at length. But basically, what I would say is that right now in ROS, if you don't have real-time constraints, you can do a lot of things that you cannot do with ROS-Control. So things like expressing like a computational graph, or chaining controllers, introspecting inputs and outputs between boxes in your computation graph. So there's many things that would be very interesting to do that the ROS-Control infrastructure doesn't really allow you to go further than a certain point. And what we're going to be talking about in ROS-Con is how the ROS2 project could help to make this happen.
And the other question was, are there any Cartesian space controllers in ROS-Control?
Yes. I would say that in the official ROS controllers repository, there are none. But I know that there is at least one implementation for Cartesian control of a single end effector that I've seen in use. And also we have a proprietary implementation of whole body control that you can use multiple end effectors and subject to prioritization, and it's quite complete, but it's also proprietary.
Okay, thanks a lot, Adolfo.
Okay, and thank you all for listening.
So we're going to go on to our next talk from Jorge Nico from Southwest. Jorge, if you're on, go ahead, please.
Yes, how you doing, everyone? This is Jorge Nicho from Southwest Research, and today I'll be talking about the work that we've been doing over the past few months on the STOMP motion planner. So the motivation for this work is mainly to provide an alternative to the planners that are currently available in MoveIt. We believe that the current planners are very useful, but we also think that for a lot of planning problems, STOMP could provide a more suitable option. So some of the advantages of the current planners in MoveIt is that they can be used immediately right out of the box, meaning that if you have a robot in some environment components defined in a URDF file, it's pretty easy to take that and generate a MoveIt config package, and at that point you can start generating motion plans for a robot. Most of these planners can solve simple planning problems very quickly, and some of them can even solve more difficult planning problems, such as those that involve multiple obstacles between the start and the goal pose. Or they can even handle dynamic obstacles, such as those that can be generated from sensor data and represented through octomaps in the planning scene. Some of the challenges with the current planners is that most of the time they tend to produce jerky trajectories or introduce unnecessary robot movements. So it makes it almost a requirement to have some kind of post-processing step for smoothing. Although smoothing doesn't, or these post-processing steps don't necessarily move all the inefficiencies and the generated trajectories. And another challenge is that sometimes or whenever there are special conditions within a planning problem, it's difficult to tune the behavior of these planners so that they can meet those special conditions. So what is STOMP? STOMP stands for Stochastic Trajectory Optimization Planner. As its name suggests, it's an optimization-based planner which can generate smooth, well-behaved, collision-free motion paths within reasonable time. The original work was done by Mrinal Kalakrishna and Sachin himself, with several other contributors back in 2011. Unfortunately, the source code for STOMP was discontinued more than 2 years ago when the transition to ROS Hydro, and along with that, several components of the MoveIt core library were also discontinued and moved into the MoveIt experimental package. So basically, STOMP and those components of the MoveIt core library have been in a non-functional state for about 2 years or more. Sorry about that. Okay. So some of the strengths of STOMP is that, as I mentioned before, it's able to generate smooth, well-behaved motion plans in reasonable time. So this eliminates the need for post-processing smoothing, since smoothing is itself a goal in the optimization process of STOMP. In addition to smoothing and obstacle avoidance, STOMP can accommodate other objective functions such as torque limits, energy considerations, and tool constraints. One neat feature about STOMP is that it can accommodate cost functions that are not non-differentiable, meaning that in the mathematical sense, if you were to take the derivative of your cost function, you still get a function that has no discontinuities. A lot of times that is difficult to produce. So fortunately, STOMP doesn't require you to adhere to those requirements. And for instance, if you were to have some kind of rule that defines energy consumption in your robot, you can define those rules as a set of heuristics, and as long as you wrap that into the proper class interface, STOMP can use that cost function as part of its optimization process. Another thing that STOMP does in order to be more efficient is it uses distance fields and spherical approximation of the lengths of the robot in order to compute distance queries and collision costs. And this is more efficient than doing the alternative way, which would be to actually use the full geometry of the robots in order to provide the same results. So what's the current status of STOMP? So we managed to update upgrade the code, the source code of STOMP, so that it uses the latest in the MoveIt library, or at least what's in Indigo at the moment. We've also managed to make it into a motion planning plugin, which can be loaded by the Move Group node, and that allows STOMP to be invoked from the motion planning panel, which is available. So you can essentially call STOMP the same way you would call any of the OMPL planners that are currently available to MoveIt. One advantage is that it can be configured to meet special conditions by the use of a YAML file, and there's no need to provide extra files or support information for STOMP, since it loads the robot environment information from existing files such as the URDF, which contains your robot and environment definition, and the SRDF file, which is generated from the MoveIt setup assistant. Currently, STOMP only optimizes for obstacle avoidance and smoothness, but as I mentioned before, there's a possibility of adding extra objectives that can be taken into account in the generation of the motion plan. And that is the link to where the code is at the moment under ROS Industrial. So right now, I'm going to go ahead and play a video which shows the performance of STOMP in comparison to the current MoveIt planners for the same planning problem. I'm not sure if you'll be able to see the video here. So at the bottom, you will see the planner that was used to generate the motion plan, which is being executed.
I don't think so.
Okay. Maybe each individual can click on the link and watch the video. And like I said, what you're watching is essentially a number of, yes.
You want to share the screen.
Okay. I think it'd be easiest if
Yeah, I think it's
click on the link.
Yeah.
This is a short video. It's like 1 minute long. Okay, well, you can, there's another video below that first video that I presented, which shows STOMP planning on their various planning scenarios. You're welcome to watch that whenever you get a chance. So the future work that we'd like to do on STOMP is to allow for extra objectives to be accommodated in the optimization process, such as dynamics, considerations, energy consumption, and path constraints. Also, there's a lot of residual bit code since STOMP was written for an older version of MoveIt. There's code now that can either be upgraded or probably removed since it's no longer needed. And another thing that we'd like to work on is better integration with the MoveIt pipeline. So maybe have automatically generated files through the MoveIt setup system that supports STOMP. So it could be easy to switch between STOMP and OMPL. So one challenge at the moment is that if you have a very complex robot or environment in your URDF, or there's a lot of detail in the models, the distance field can take up several minutes to generate. So it'd be easiest to perhaps serialize, basically generate that distance field once, save it in some sort of file format, and then load it at runtime whenever MoveIt and STOMP are brought up. And then something that we haven't really tested is the handling of dynamic obstacles such as octomaps, which hold sensor data, or the inclusion of extra geometries that can be attached to the robot links. And with that, there's my contact information, and once again, the link to the source code for STOMP, and I'll be happy to answer any questions.
So Jorge, there was one question asking whether there are tutorials.
So we don't really have a tutorial at the moment, but we'll be upgrading the GitHub page and put some information as to how to use it. However, the code right now has a demo package, is a MoveIt config package. So if you run the demo launch file, you'll be able to actually run or plan with STOMP right away.
Thanks, Jorge.
All right.
Thanks a lot.
Okay.
Those are great improvements.
Thank you.
So we're going to go on to the next talk from Dina Yukim at the University of Girona. And she's going to talk about an application of MoveIt. So this is for underwater robotics. Dina, please go ahead.
Hello everyone, this is Dina Yukim, and I'm going to show you an application of MoveIt in the underwater domain. And this was done for my master thesis in the University of Girona. So if we check the current status of the underwater, we will find that the autonomous underwater vehicles are mainly doing survey and exploration applications, while the interventions are left for the remotely operated vehicles. And this is due to the complexity of the intervention. But with the increasing necessity of the intervention in the oil industry as well for rescue application, it's becoming really challenging to try to investigate this intervention in a more autonomous way. And if we check the state of the art of the autonomous underwater vehicle, we'll find really few projects that have done intervention autonomously, like Sovereign and Trident project. And there are 4 more projects who actually did a common task, which is valve turning, and this is inspired by the oil industry. And we can see that 2 of these projects did it on a docking base, while the other 2 did it on a free-floating base. And we will see that we use mainly this scenario of valve turning in order to validate the use of MoveIt in the underwater domain. So as far as we know, that MoveIt has not been yet used in the underwater. So this was the main objective of the project, is to investigate the suitability of using MoveIt in UVMS to perform autonomous intervention tasks. So just to give you a brief introduction about the system that I have been using. The system has 2 parts. The first one is the AUV, which is called Girona 500. It's a lightweight vehicle and it has 6 degrees of freedom. and it has 6 degrees of freedom. 2 of them are passively stable in roll and pitch. And also it uses AKF SLAM in order to localize itself in terms of position and linear velocity. While for the angular velocity and the orientation, it uses an EHRS system. Also, it has a cascade controller where the position and velocity and torque are connected to each other. And the other part is the arm, which has 4 degrees of freedoms that can be controlled in position, and it has also a passive gripper. So the first step in order to integrate MoveIt with a Girona 500 was to model the Girona 500 in MoveIt. And this is done, as we know, in the URDF. So the first step is to define the physical and the collision properties of MoveIt, and this is done mainly in the link tag. And as we can see here, we have the results of the modeling the system. The first one is showing the normal model, and the other one is the collision model. And the second step is mainly related to defining the kinematics properties of the system. So for the kinematics properties, we finally decided to have the whole system as 8 degrees of freedoms. The first 4 degrees of freedoms are concerned with the AUV in order to define the X, Y, Z, and U. Roll and pitch were defined as fixed, as I mentioned at the beginning, because the system has a fixed in roll and pitch. And the other 4 degrees of freedoms are concerned with the arm. The other part of the model, which is in the SRDF, and in the SRDF, we have to define the collision between successive joints, if they are allowed to collide or not. And the other part is to define the planning groups. And these planning groups is a set of joints that act together as a single group in a planning task. So in our case, we had 2 planning groups. One of them, it has the 8 degrees of freedom of the system. And this was the main group that was used during the validation task. And the other part is concerned with the gripper. And since in our case, we had a passive gripper, so we had only one fixed joint. For the kinematics and planning plugins, we use only the default plugins, the KDL for the kinematics and OMPL with RRT Connect for the planning. In order to take profit of MoveIt, and because the system has its own controller, we had to do a controller interface between MoveIt planning output and between the system controller. So this MoveIt planning controller plugin takes the output of the planning manager, which is a robot trajectory message, and this trajectory has several points for the planning to be executed. And each point has 8 degrees of freedom, as I mentioned at the beginning. So the controller was mainly splitting this 8 degrees of freedoms into 4 degrees of freedoms for the AUV and 4 degrees of freedoms for the arm. And in order also to be sure that we reach, that the actual system reached the required accuracy, we had to implement a feedback loop that takes the current state of the joint from the system controllers and compare them with the required points. And until a certain precision is reached, we keep sending the same message again and again. As I mentioned at the beginning, that the valve turning task is becoming kind of benchmark for the autonomous underwater intervention, so that's why we decided to use it to validate the use of MoveIt. And the intervention task has mainly 3 steps. The first one, what we call detection. In this case, the goal is to detect the panel where the valve is fixed. And this panel also acts as a landmark in order to help the AUV to localize itself using EKF. So once the panel is located, the AUV is able to localize itself, and also we are able to compute the position of the valve, which is going to be the position of the manipulation task. Then we move to the next step, which is called the inspection. And in the inspection, the main goal is to home the AUV in front of the panel. Since in the detection phase that we are not sure about the position of the AUV when it was detected, so maybe in this case the position was not really well estimated, and then the intervention task can fail. So we had to add this step in order to be sure that the estimation of the position is quite accurate. And once this is done, we move to the last step, which is actually the manipulation, and this has 3 sub-steps. The first one is to do the approach at 30 centimeters far from the valve. And then we do the actual grasp, which in this case is just touching the valve. And then we do the final step, which is turning the valve. And also to take profit of MoveIt, we added the obstacles, virtual obstacles, in different phases of the manipulation task. The other thing that we investigated also is doing a grasp analysis, because whenever we are talking about manipulation, the first thing that comes to our mind is how we're going to choose the position and orientation of the manipulation. In our case, we cannot play so much with the position. What we can really do is play with the orientation, taking profit of the variability we have in the passive gripper. So we did a sampling for the orientation space, and then we select the candidates that are suitable for the scenario that we are doing. For example, in our case, we cannot really do a valve turning from upper or lower orientation. And then we do another filtering based on the collision avoidance. And then finally, if we end up with more than one position, we had to choose between them given certain quality measure. And in this case, we use the manipulability index in order to define which one has a better manipulability index for the task. And in this slide, we see just exactly the same steps, but this is a simulation of the system in MoveIt. And as we can see in the last row, that we had less options in the case of having an obstacle close to the manipulation location. And this is a high-level overview of the implemented system. The two nodes that are in blue that are the one dealing with MoveIt, the planning manager and the controller, and the yellow one are the one that the real system controller. And then we have the synchronization node, as I mentioned at the beginning, between the system controller and MoveIt planning. And this is a more detailed, just in case you are interested with all the ROS nodes and messages that has been implemented. Since we had a bit more time, and this is really shows the power of MoveIt, we decided to do a more advanced grasping task, and the passive gripper has been replaced with a 3-finger hand. And in this case, we try to do a connector plug and unplug. And in this case, we just need to modify simply the model of the gripper and replace it by the 3-finger model and adapt the system like really quickly. And we were able to do this task also successfully. I'm not going to really have so much time to show you the videos, but the links are available here on the lab YouTube channel. So just to conclude, that MoveIt has a really good potential in the underwater manipulation, but we really have so many other things to check. For example, to integrate with the perception part in order to have update of the environment dynamically and be able to test with real obstacles, and maybe also do path planning benchmarking. And finally, do more advanced grasping tasks like for assembly, for example. And these are some references, and thank you so much.
Thank you, Dina, for that's fantastic work. There's one question asking about simulators for underwater vehicles and whether there's any simulation library.
Yeah, actually, I just didn't mention this, but one of the steps before going to the real system in the water tank, we had to do simulation, and there is UWSim, which is really common simulator for the underwater, and it's open source. You can download and you can adapt it to your system.
Okay. There was also a comment asking whether you can share the YouTube links. So once we are done, if you can share the links to the video, to the videos in the chat, that would be great.
Sure.
Somebody has asked if you can name the simulator once again.
UWSim.
Are there particular things that you would like to see in MoveIt that would help in these kinds of applications?
I mean, so far everything was kind of fine. We just need to work more on the perception part, because it would be really great to have real obstacles in the environment underwater and see how the planning will handle this, since there is so much disturbance in the water.
Okay. Did you have any trouble coordinating the motion of the UAV? The AUV and the arm. Do you have to do any kind of stabilizing control while you were moving the arm?
No, the thing is, what we had is we have only a single system. Like, we modeled both of them a single system, which leads that the AUV was quite slow because the arm was quite slow. So this is one of the things that we would like to work on, is to separate both, and then we will need to handle the controller and stabilization between both. But in this case, it was only one system. Then it was quite stable.
Yeah. There's another question asking if you would use Gazebo for underwater apps.
I mean, so far we didn't get into this, and I'm not sure if it can really add any value, because mainly I use the RV simulator provided by MoveIt in order to first validate the system and the modeling and everything, and then I went to UWSim, which was quite ready for the underwater.
Okay. Well, thank you very much. This is fantastic work. It's a very different application of MoveIt, and we certainly like it.
Thank you.
So we're going to move ahead to the next talk from Stefan.
Yes. You hear me? Okay. So yeah, my name is Stefan Kohlbrecher. I'm a PhD student at TU Darmstadt, Germany, and I'm with Team Vigor and was responsible there for the onboard software. This is joint work with the people you see on this slide here. Yeah, Team Vigor is an international collaboration, Track the Atlas team, made up of quite a few institutions, and what probably is a little bit different about our team than the others is that we span like 9 time zones from California to Germany. The DRC, you probably heard about in the media. For the teams, it was also very challenging because it had a highly compressed timeline, competition events every few months, and for that reason, it was very important to not to try to reinvent the wheel, but leverage open source software, and that's why we also used MoveIt. MoveIt has also been used by several other teams. I know some Track Labs guys, for example, are on this call, and I think they also used it. WPICMU used it, and also a few other teams. So this is not exclusive to us, obviously. Yeah, what are the requirements we look at for the DRC? We have to do manipulation, of course. We don't want to have collision-free planning, so we don't bump into things with the arms of the robot. We want to be able to do Cartesian paths because, for example, if you open a door, or if you want to drill a hole with a drill into a wall, then you need Cartesian paths. We often have manipulation in contact with the environment, which is a little bit different from normal pick and place where you just have brief contact. We often have cases where you have longer contact. And of course, we always want to maintain stability and not have the robot fall over. In terms of commanding the robot, we want to have a range of options. Basically sliding autonomy from operator and operator control station based teleop to operator object template and affordance template based task level control, and also in the ideal case fully autonomous control using a behavior executive. The robot we used is the Boston Dynamics Atlas robot. It's hydraulically actuated, very heavy, has 7 degrees of freedom arms. And the good thing was that that Boston Dynamics provided an API that allowed walking and stepping control and balancing. So to some extent, we could decouple the upper body planning problem from the low-level balance control, and we leveraged that quite a bit. I hope this is readable. If it's not, this is basically how our MoveIt setup looked like. We have Move Group, the standard Move Group system running. We have all the standard Move Group plugins running simultaneously, and then we have some special plugins we developed for our use cases that I will introduce later. One thing that we noted is that the MoveIt setup assistant is very nice, but in case of our robot, we had different hand options, and we had to be able to quickly change between those. So that basically gave us a combinatory explosion of configs, and you don't want to run tons of setup assistants all the time. So what we ended up using is using Sacro macros to change configs, and I can sort of recommend that if that happens to you too, it's doable. And on some slides, I have these links down there which directly bring you to the GitHub thing to the GitHub repo that is relevant. Yeah, in terms of sensing, we implemented our own Octomap updater. You might ask why that is, because there's the point cloud Octomap updater. It does the same thing like the existing updater, but it also provides filtered LiDAR data for the overall system while maintaining information about the laser scan structure. If you look at the overall system briefly, you have the updater there on the left. but we have separate ROS masters because we have highly constrained communication and only intermittent communication between the operator control station and the onboard system. And for that reason, it was very important for us to filter the data, but still be able to compress it very well. And that's why we rolled our own LiDAR updater. In terms of planning capabilities, we made a separate Move Group plugin that basically replicates what MoveIt already can do, but also supports different kinds of motion simultaneously. So you can specify joint goals, you can specify Cartesian goals, you can specify Cartesian waypoints, and also specialized circular motion, because that's often used in the DRC for driving, for turning a wheel, for opening a door, for drilling a hole in a wall. We also added a feature of being able to specify a reference post relative to the end effector, because if you want to drill a hole in the wall, you want to specify the drill bit of the drill as a reference frame. And also, we can also constrain the joint limit selectively at runtime. That was important for this humanoid system. On top of the planning system, we implemented an object template approach that allows the operator to place objects and then plan relative to these instantiated object templates. The template library contains geometry information, mass information, grasps for the object, and stand poses. And yeah, basically, you have your object and sensor data, and then you align it. And then you can act upon basically this instantiated object. Yeah, the other thing we use is for pre-planning, because your humanoid is always at risk of falling over, so you want to check first if things work. We use this virtual ghost robot. This is kind of similar to the start goal state visualization in the MoveIt Arvis plugin, but it's integrated with the object template approach, so you can snap your end effector to a grasp pose, and then you can move your ghost robot around, for example, and pre-plan stuff. You can move the ghost robot to stand poses relative to object templates. You can selectively constrain IK joint limits during pre-planning. And based on the ghost robot state, you can send low bandwidth planning requests directly from the operator control station. So the ideal workflow looks like this. Your robot is standing somewhere, there's an object. You place the object template, then you can move the ghost robot to a stand pose relative to that object template. You can figure out, play around with your placement of your robot and see if it works kinematically. And then when you're satisfied, you just send a footstep plan and the robot walks there and then can pick up the thing. Yeah, there's some other stuff we did, selectively slowing down trajectories. Sachin already talked about that previously. We also noted that the parabolic time parameterization can have acceleration spikes, and we have a cubic time parameterization approach for that, which right now still lives in a MoveIt fork, and yeah, probably needs some work before it can go into upstream. What we also have is we can switch between MoveIt and MIT's Drake planning framework on a per plan request basis, because we wanted to have whole body motions, but didn't end up using them in the DRC actually. Yeah, there are some references and videos here. There's a YouTube playlist that shows a few instances of the system in action. So to quickly conclude, MoveIt provided the required basic manipulation capabilities we were searching for. It was very easy to integrate and also use it as a library in other parts of the system beyond pure planning. And the very good thing about it is the sensor-based collision avoidance. For humanoid robots, there are some potential areas for improvement. Of course, consideration of balance constraints, whole body planning, optimization-based planning. We already heard about that a little bit. And also, I think workspace analysis is, there's still work that can be done there. And also inverse reachability, figuring out where my robot should stand so it can grasp things. Everything I talked about is available on GitHub, and there will be much more in my ROS-Con 2015 talk, where I will also talk about the wider system And our plan is at the ROS-Con talk to have everything available for download for everyone, so you can basically run the whole thing in simulation. Yeah. Okay, that is it from me. You can contact me via email too. And yeah, I'm open for questions.
Thanks a lot, Stefan. That's fantastic. You mentioned using Zacro to generate the SRD. Is that something you're going to put back in upstream?
Well, I mean, it's you can do it, right? It's you can. It's an option. You basically generate a config with. What I did is I generated a basic config with the setup assistant, and then I did some Zacro stuff to integrate the different hand options. It's not at this point. It's not a separate package. It's just work. But yeah. Yeah, so, but we could think about like formalizing it and making it easier, I think.
Yeah, okay. And the other question is about the, so there's a question saying, now that the DRC is over, what types of problems are you working on now? Are they roughly the same as the DRC problems?
I think the DRC was very challenging, of course, but I mean, there's still a lot of work to do till humanoid robots can go into a Fukushima type disaster and reliably do stuff. And I think until we are there, we have plenty of research to do. So we have a Tor-Mang robot here in Darmstadt, and we are actively working on improving it across the board.
There was a question about, again, about the SRDF. So one quick comment saying a quick tutorial about the Zacro SRDF would be awesome. And then there's a question about how does that deal, how does your use of Zacro, how does that deal with the collision matrix?
Yeah, that's a little bit tricky. If you, I mean, everybody can look at the package. You define some Zacro macros, then later you call them, and you can do quite a few things with that, but it's probably not expressive enough to cover every case. Yeah. So.
And just to finish off, a question about your use of parabolic parabolic splines. Is that something that you're hoping to get upstream?
Yes, I have to. I wasn't the one who contributed it. It was David Connor, so I have to talk to him to take a look back at it and see if it makes sense and evaluate it for general use. But it would be something that would be beneficial, I think, because there were also on GitHub there were quite a few comments about that.
Okay. Looks like there are no more questions for you. Thank you very much for a fantastic talk and a great application.
Yeah, thank you for having me.
So we're at the last talk for today. That would be Jackie Kay from OSRF, and she's going to talk about ROS 2.0, Gazebo, and you. Go ahead, Jackie. Jackie, we can't hear you. Jackie? It looks like we're having some technical difficulties with Jackie. Jackie, if you're having issues with your computer audio, you can also call the toll-free number and use that instead. In the meantime, if anyone has questions for the other presenters, please go ahead and ask them. Or if you have general questions about MoveIt or any of the packages that you're seeing today, please go ahead and ask those. So there was one question: are there any learning from demonstration-based planners in MoveIt? The answer right now is no. There are no planners like that, but there's other. There has been other software in ROS or other packages in ROS that deal with that, it's something that would be nice to bring into MoveIt as well. So there's a question asking, how good is the speed of STOMP, especially when updating the environment, the Octomap? Jorge, you want to take that? Jorge, we can't hear you.
Can you hear us now?
Yeah. So Jorge, the question was, how good is the speed of STOMP when updating the environment, the Octomap? So it looks like Jorge is having trouble getting on, but in the meantime, Jackie seems to be ready. So Jackie, why don't you go ahead with your talk?
Yeah, thanks, Sachin. And thanks everyone for coming out today and sticking around for this talk. So as you know, as you probably know, OSRF doesn't directly support MoveIt. We focus our efforts on the lower layers of the stack in ROS, as well as working on Gazebo. So I'm going to focus my talk today on recent development and future features in ROS 2 and future releases of Gazebo, so 7 or 8, and how that might affect your work as a member of the MoveIt community, which extends to people doing really interesting heavy-duty work in motion planning and manipulation. So just kind of a brief overview. I'll talk about ROS 2 first, give an intro for anyone who would like to know more about ROS 2 or isn't up to date on the developments of that. I'm going to focus in on, I think, what I thought was the most relevant planned feature for ROS 2 for manipulation, which is real-time performance. And Adolfo's already talked a little bit about real-time and ROS-Control. Then I'll switch gears, talk about Gazebo, and leave a little time for questions. So ROS 2 is a very exciting project that will allow us to introduce lots of new features that will support basically sectors in robotics that are not supported by ROS 1 without breaking API in a massive way in ROS 1. Some of those new features include building on top of DDS, data distribution service, which is a different network protocol that's used in ROS 1, and that will allow ROS nodes to be fully distributed, so there's no more need for ROS core. There's nodeless will no longer be a separate abstraction from nodes. So, for example, this robot looking at a point cloud in this picture, the code that it's running looks exactly the same as kind of standard ROS 2 code, but behind the scenes, there's an efficient inter-process communication pipeline that's zero copy and will improve performance a lot, and also ease of use for that use case. So there's going to be kind of a separation of the threading model from the node model, if that makes sense. So basically, the number of threads, or single or multi-threaded, will be controlled more by the user than it is in ROS1 through the executor abstraction. And also, from day one, we're trying to support embedded systems and running ROS2 on small, maybe SMT32 microcontrollers. So you can read a lot more. Sachin's provided. This is actually a generic Google Images image that I found regarding your question, Sven. But if you're curious to read more about the kinds of embedded systems that we're trying to support right now, yeah, thanks. There's a tutorial. The link that Sachin provided is some more information about the kind of work we're doing on embedded systems. So a lot of the work that I've been doing this summer is looking at how we're going to make ROS2 real-time compatible. So I highlighted this because real-time controllers are necessary for creating responsive feedback, which is really important in whole-body motion planning problems and manipulation for if you have tactile feedback, for example, and also in kind of critical situations where you need to be efficient and responsive, such as industrial engineering or industrial manufacturing, or even aerospace missions or aerial vehicles, autonomous aerial vehicles. So we're trying to bake in real-time safety from day one in ROS2, unlike in ROS1, where there's a number of performance issues. And again, I'm not going to go into too much detail about this in this talk. Actually, as Adolfo said earlier, we're presenting at ROS-Con. We're going to have a long talk about this issue. So look forward to that. It will be available online if you're not going to ROS-Con. So I'll give an overview of how we implemented this in the release we put out on Monday, which we're calling Anchor. That's basically our kind of minimal alpha release of ROS2. So there are configuration options that are exposed in the client library API that control things like your memory allocation and also your threading model. So this is a single-threaded ROS executor, or ROS, basically a thing that manages all the nodes and puts all the jobs that come in that need to be handled by the nodes and queues them in a single thread, rather than having multiple threads that pop up when you have callbacks. We're not using, in the client code, we're not using any standard library synchronization primitives or threading, and any blocking that we do is based on the DDS implementation. So it essentially waits for an update to come in via DDS. So if you trust your DDS implementation to be real-time safe, then the ROS code will be real-time safe. And this allows you to not block through when you need a real-time update to come in. So the links that I've provided are to a tutorial for this demo, which is a simple inverted pendulum balancing simulation. It's very minimal right now, but this will hopefully motivate things like a humanoid walking problem or difficult control problems that need to be real-time safe. And in that demo, I show that there are no runtime allocations while the nodes are spinning. There are allocations in the beginning of the program while everything's initializing, and at the end, there's deallocations. But essentially, this is to show that there'll be no non-deterministic blocking due to allocations. Should I stop to answer these questions, Sachin, or should I address them at the end?
Probably address them at the end.
Okay, cool. So I'll switch gears to talk a little bit about Gazebo. Our work on the DRC has enabled us to make a lot of improvements recently. Some of that is improving the physics engine support and both the features we integrate from the physics engines we support and also the stability of the physics code. And that was really important as we were simulating things like Atlas walking, which is a heavy-duty problem for physics simulation. We also, for another project that we're doing called Haptics, which is a prosthetic arm simulation project, we're developing support for a lot of teleoperation devices and kind of virtual reality devices like the Oculus and the Razor Hydra, which is a 6 degree of freedom magnetic motion controller. And we see that as kind of helpful for cases where you're teleoperating a robot. It could be really useful in manipulation research where you're learning trajectories that are made by a human. They could go directly into Gazebo and directly into ROS. So again, we've supported the DRC, but we're also supporting the first high school robotics competition. We're hoping to make Gazebo the primary or an option for simulation for that, and also for RoboCup. We've recently implemented, we've improved Gazebo logging, and we've implemented playback, which is so playing back or restoring state from the log and starting from that point and replaying simulation, which is another tool I think is really invaluable in research. And we've also recently implemented torsional friction, which for anyone who doesn't know, it's friction due to torque on contact with the surface rather than linear forces. So that could be really key also in simulating like certain contacts or certain interactions with objects. So looking to the future, we have a really exciting new challenge that we're supporting, which is the NASA Space Robotics Challenge. Some teams that were involved in the DRC will probably move on to participate in the SRC. We'll have a full model of the NASA Johnson Space Center Valkyrie, and that'll probably also lead to a number of exciting papers and new challenges in simulating manipulation problems. And another project that we have on our plates that's gearing up is thinking about simulation validation, which will hopefully improve the realism of robot models simulated in Gazebo, and also the realism of Gazebo itself, and how faithfully we can duplicate physics and also duplicate robot controllers in Gazebo. And another thing that we'd like to support is deformable objects. Currently, Gazebo only simulates rigid bodies, but if we could extend that to soft objects, flexible objects, a lot of exciting research, I think, can come out of that. So that's about it for now. I think we're probably way over time, but I'll take questions now.
So Jackie, that's fantastic. Thanks for giving us an update both on ROS 2.0 and Gazebo. There's a few questions. When is a stable ROS 2.0 version planned, and how stable is the alpha of ROS 2.0?
So essentially, we don't want to rush anything, of course, and also measuring stability in code is hard, but we have a lot of tests that show that pub sub is very stable. Services are implemented and tested. Parameters are also implemented and tested. The demos are all stable. Essentially, those are kind of the focus point of our work. But I think that it's not an issue of stability, but a fully featured ROS 2. There's still a lot of features that we'd like to implement to catch it up with ROS 1, and that's going to be an ongoing project, certainly. But I imagine there will be another major, exciting release, perhaps the beta, next year.
Okay. The other question was, does ROS 2.0 go with Gazebo 5.0?
We haven't started on ROS 2 Gazebo integration. It's just a matter of writing a new Gazebo ROS plugins, essentially. So it will probably pair up with a future version of Gazebo, like Gazebo 7 or Gazebo 8 even.
Okay. There's a question about, does Windows support? So does Windows 8 support imply Windows 8 and up, including 10?
We haven't started looking at Windows 10 yet. Yeah, Gazebo you can build Gazebo from source on Gazebo 8. and 7, right? Gizebo 7 and Gizebo 8, or sorry, Windows 7 and Windows 8. Yeah, I'm a Linux person through and through, so I'm not the person to ask about Windows support on Gizebo, but
Okay.
yeah.
There's a question, does real-time and ROS 2.0 require a real-time operating system?
Right, so basically real-time performance, if you have like a non-real-time safe operating system, then your code technically won't be real-time. So like the default Linux scheduler is not real-time safe. But so we've been testing with RT preempt, which is like a soft real-time system. So essentially you have to, you do have to change your operating system to handle things like thread scheduling.
Okay. Will ROS 2.0 use URDFs?
Yeah, so I actually was thinking a lot about discussing this in this presentation, but we haven't really started the conversation on how we're going to improve robot description formats yet, because we're focusing on this very low level of the stack rather than the high level that a lot of people here are interested in. I think there's, I'm really welcome to feedback about how we might change URDF, Zacro, SRDF, or maybe those are all perfect and we'll stick with them so that we don't break a lot of code. But please, if you have ideas about how that's should be developed, then email the ROS-SIG-NG ROS mailing list, and we can start a conversation about it. Or email me directly. All the emails are here on this slide.
Is there a list of features that the community could help OSRF tackle for ROS 2.0?
Oh, for ROS 2.0 or just ROS in general, Ian?
I think he meant ROS 2.0.
Oh, okay. Sure, yeah. Thanks for the offer. Yeah. Definitely testing the code that we've put out and giving your feedback on that would be awesome. We collect issues on GitHub in the ROS 2 organization. If there's anything there that kind of strikes your fancy, or specific things you want to tackle, but I mean, give me some time and I'll come up with a list for you if you're interested.
I think the last question for you, will existing packages work with ROS 2.0, and how big of a switch will it be?
Yeah, so we have a lot of documentation about migration on design.ros2.org and also on the wiki. So there's we've implemented for that alpha release a ROS 1, ROS 2 bridge.
Okay.
So that basically enables you to pass messages between ROS 1 and ROS 2. And we also basically have created a guide of describing API differences, like a changelog, or kind of a high-level changelog for conversion.
Okay. I think there's one last question saying, does Gazebo allow the robot model to change at runtime in terms of adding and removing links?
Yeah, but it's difficult, is kind of the answer I give a lot of people. So basically you could write a plugin and use the physics interface to dynamically add and remove links to your model, but that it might have weird effect on physics. We do this for the model editor and a couple of other tools. So, there's not a dynamic way of doing it through the GUI besides using the model editor.
Okay. Thanks a lot.
Thanks a lot.
So we have time for a few more general questions for, so if you have questions about MoveIt, about the direction that you'd like it to go, if you have questions about any of the other stuff that you've seen today, we have, I know we're over time, but we have like just a few minutes to go over that if anybody has questions. No questions. I guess it's all perfect. Oh, there's one question asking, is there scope of using the ROS-Control manager instead of MoveIt controller manager? So I'd also just left the meeting, so I can answer that. It's definitely something we'd want to look into. They kind of do slightly different things now, but one of the things we would like to see more is better integration between MoveIt and ROS-Control. So, you know, the number of config files are limited. The amount of extra stuff that you have to do to get the two connected is much less. So that's something we're definitely starting to look into. There was a question of where will all the slides be posted. We should be able to put them up on the MoveIt website, but that might take a little while. And the movies we should be able to post it on YouTube soon after the meeting is over. I'll send out an email for both these things. I'll send out on ROS users and on MoveIt users. We definitely like to. So there's a question about, is there some extended documentary about the planners in MoveIt and OMPL? Mark, do you want to take that one?
Well, there's the OMPL website, but that doesn't talk much about the integration with ROS. So I think the MoveIt website is probably the best resource for trying to find out how OMPL is integrated with the rest of MoveIt.
Yeah, so if you're looking for information on how MoveIt talks to OMPL and how MoveIt uses planners, you should go to the MoveIt website itself. If you're on the OMPL planners themselves, then look at the OMPL website. So we definitely are looking to make this a regular event. If you guys have suggestions of where this could be co-located with a conference or a workshop, please do let us know. We will make it a kind of a combined online plus real-time live event so that as many people as possible can attend. And as usual, if you have questions, if you have things that you can contribute, please do join the MoveIt mailing list. That's the email. You can also get it from the MoveIt website. Please send us news. So if you have movies of projects, if you have movies of robots, even new robots that you've integrated MoveIt onto, please let us know. And with that, if there's no more, thank you, Mark, for saying that's the most enriching online meeting you've attended. If there's no more questions, I think we're done, and we will I think some of the people here will probably meet each other at ROS-Con. Otherwise, we'll let you know when the next meeting happens. Thanks a lot.